All right. Okay. All right. So this makes sense. Does this make sense to you? Hope this makes sense to you, right? All right. Now this is your P, and this is your diagonal matrix, right? All right. Look at this. So this is your P. So just imagine this. This is your P, and this is your V. Column one vector, column two vector. Okay. And you have, say, lambda 1, right? Others are 0. Let's imagine that. So when you multiply this one together, these two together, this one times this one times this. All right. That means you get something lambda v1 all the time. Other columns are equal to 0 if you have 0 all the other thing, or all other values of the diagonal, right? So if so this is lambda 2, then the second column should be lambda times v2, and third column would be lambda 3 times v3, and the final column is lambda n times vn. So are you with me, or do you understand this? So just try to prove this one for 2 by 2 or 3 by 3 matrix. Then you will realize this is true. This is true. If you cannot imagine this one, right? These are column vectors. I mean, when you multiply this matrix by this diagonal matrix, you get this one. Okay. So give me your feedback. Did you understand this one here? Yes or no? Give me your feedback, otherwise tell me whether you understood or no. Clear. Okay, very good. All right. If you not do this for 3 by 3 matrix, then you will realize. So how do you do that? Take any matrix A and take another matrix P and use this column. This is V1 column, V2 column, V3 column, right? So when you multiply this one, so when you multiply this one, you can write in terms of V1, V2, V3. You will realize when you do for 3 by 3 matrix, this would be A, V1. So column again. So first column of AP matrix. The second column of, let's give, here we give I have given a name AV1. That's all, right? So this is the second column AV2. This is the third column AV3. That's all, right? Okay. All right, then these two matrices are identical. That means this column should be equal to this column, and this column should be equal to the second column. This, yep. All right, that means in general, yep, that means A V I should be equal to lambda I V I. This one is true for all I from 1 to n. I from 1 to n, right? Okay. Oh, this looks lambda looks like, yeah, lambda looks like eigenvalues for A. So if I say this one is non-zero, then I can say lambda is an eigenvalue of A. So here P is invertible here, right? So if one of these column is equal to 0 column, what happens? It is not invertible, because if one of these vi's is equal to 0 column, 0, that means one of I is equal to 0. That means 0 column. Yeah. So column vector, right? So what happened to the determinant of P? Determinant would be 0. We know P is invertible. Then these are non-zero columns. Non-zero columns. Then VI's are non-zero vectors. Therefore, this lambda is eigenvalue of A, and the corresponding eigenvector is Vi. These are Vi is the corresponding eigenvector. So A has an linearly independent. So you can show this one is linearly independent. So here I don't show that one because you haven't learned linearly. So what linearly independent set, right? I will explain that later because I don't have time. So other way around, let's assume A has, let's consider the right hand side is true. A has n linearly independent eigenvectors, right? Okay, these are the linearly independent eigenvectors. Okay, and the corresponding eigenvalues is lambda i's, right? You can rewrite this one in the similar way. You can show this one is true, and here vi's are linearly independent. Then P matrix is invertible. If these columns are linearly independent, you have n number of linearly independent columns, then you can show P is invertible, or this one is true. Therefore A is similar to this diagonal matrix. Therefore A is diagonalized, right? This one is true. So in exam, you don't get this type of proof, but you have an idea about what this theorem says, right? Right. So if A is diagonalizable, because you are doing applications, right? You have to apply these theorems to the real world. That's the thing. That's because you are doing industrial, financial mathematics. You have to apply theories. So if you follow pure math stream, so you have to consider these proof. You have to understand these proof very well. Right now, you are applying these theorems to the real world, right? Practical problems. All right, A is diagonalizable fan only if A has n linearly independent eigenvectors. All right, that's right. To understand these theorems, I will give some problems to you. I will upload a set of problems to you, right? So I think you have a lot of time. Just try to complete those problems, then you can grab these theorems from now on. Don't wait until the exam, right, to understand these things, right? Try to understand these things from now on, then your exam would be a piece of cake for you, right? Okay, any question regarding this? Let's discuss this one as well. Diagonalize the matrix A if possible. Right, then first duty is there's a square matrix 3 by 3, then you can find quickly, you can find 3 eigenvalues 1, 2, 3 by solving this cubic equation. Find the roots of this cubic equation. Right? What are the eigenvalues? 1, minus 2, minus 2. Right? Then you can find corresponding eigenvectors. Right? For 1, let's take this one, lambda. First consider lambda 1, first root, 1. And now you find the eigenvector, corresponding eigenvector, that you can find that, right? By solving this system, homogeneous system here. Ax equal b is 0, all 0. Then we call this a homogeneous system. Then you find the roots of this, solutions to this homogeneous system, right? What are the roots? You can find infinitely many roots, and this is the base of that root, base. Then this is your eigen vector, corresponding eigenvector, Okay. Now we consider other eigenvalue. Lambda, what is the other two? Those are, these are coincide. Yep. Lambda equals minus 2. All right. This case, lambda is equal to minus 2. Okay. So plug this one in, right? No. You have to solve this system here. Here, this one. When lambda is equal to 2, you get this kind of lambda 2, I, and this is your vector, homogeneous one. Now this time lambda is 2. And you get a linear homogeneous system of simultaneous equations. Same thing, right? Find the solution to this system. The solution would be, so solution set would be this one. And these two are the bases of the solution. So for this one, for this eigenvalue, you have two bases, right? Two bases, right? Altogether, you have three base vectors, right? You can show these are independent. You will learn, I think next year you will learn this one, right? You can show these three vectors are linearly independent. v1, v2, v3, right? Therefore, from this theorem, if A has n linearly independent eigenvectors, then A is diagonalizable. All right. So this is a 3 by 3 matrix. You found three linearly independent eigenvalues. Therefore, this can be written. This one is similar to as a diagonal matrix. So what is that diagonal matrix? Diagonal matrix. This one is similar to this matrix. Lambda 1. We found these values. Lambda 1 would be, lambda 1 is plus 1, minus 2, minus 2. So this is diagonal matrix. Yeah. So A is similar to this diagonal matrix. Then what is, so how do you find that invertible P is, so you have to place these column vectors here. This is your first column of the P vector, and second column would be this, and the third column would be that one. So this is your P, this is your diagonal matrix. A is similar to this diagonal matrix, and you found the invertible matrix as well, which satisfies this equation, right? So does this make sense to you? So I will give a couple of problems today, then you will understand these things, don't worry, right? So any questions regarding? Now you can check whether the given matrix is diagonalizable or not. First duty is finding eigenvalues, then corresponding eigenvectors. If these vectors are linearly independent, then this is diagonalizable, right? So the diagonal, so you can find that diagonal matrix. So A is similar to this diagonal matrix. These lambda is are eigenvectors of this matrix, and the P matrix is your eigen. This is your first, this is your eigenvector 1. So the corresponding eigenvalue is this lambda 1, and the corresponding eigenvector is this lambda. The second eigenvalue, the corresponding eigenvector is this, and third one is this, something like that. So this is invertible. So this is your diagonal matrix. This matrix A is diagonalized like that. You can check that, right? I will give some exercises to understand that. All right, so do you have any questions? 8:15 to cover the part today. Do you have question before jumping into this section, this one? So do you have questions regarding this other one? Yep. Final theorem for all eigen, if so say this is n by n matrix, if you can find eigenvalues, you know there are n eigenvalues. If these eigenvalues are distinct or not equal to each other, then your matrix is diagonalizable. This matrix is diagonalizable. It's another theorem. So I don't talk about the proof of this theorem. Just understand. Given a matrix, n by n matrix. So you know this is n by n. Then you can find n, how many eigenvalues? N number of eigenvalues. Lambda 1, lambda 2, up to lambda n. If these are distinct, that means this one is not equal to each other. These two not equal to each other. This distinct numbers. I think you have lambda 1, lambda, any lambda I, lambda j not equal for all I, ij not equal to I is not equal to j. For all I, j, I is not equal to. So that all eigenvalues are distinct, then we say one shot. Without finding eigenvectors, without finding this, you can say straight away A is diagonalizable, right? Without finding eigenvectors, right? All right, that is the final theorem. Okay, do you have any questions? Any questions? Any doubts? Do you want more elaborations or anything? Do you need more elaboration? Anything before moving to the next one? I hope you understood this. So I need your feedback. Did you understand? Do you have any questions? Just let me know your feeling. Just so otherwise your exam paper would be hard or easy or I don't know. Understood. Okay. Okay. Yep. Depending on I cannot see your faces. That's the problem. Yep. So all right. Thank you. So let's. All right. Let's jump right into vector spaces. Right. Okay. So what is a vector space? All right. So let's talk about vectors in R. So let's talk about Rn. I think this is kind of familiar to you, right? So you have learned real number set, right? So yep. All right. This is your real number set. So this is set of real numbers. 1D, normally this is 1D. This has only one component, a number, right? Scale. This is a set of real number, non-zero set, right? Actually, we can show that this is a vector space. Let's see how, right? And if you talk about two dimensions, that means you have two axes, x and y, right? When it comes to two dimensions, all right, x and y. So in this case, this is R. You have two real lines. This one is R. So set of all elements of this plane is given by R cross R, right? So earlier you had just R. Now you have two coordinates, x comma y. Let's get this. This is your x component. You have y component because this we are talking about this one is same with coincide with similar with r square. Two dimensions. This is one dimension r1, right? Right. So this set is isomorphic to this r squared. Don't need to worry about that, right? Two dimension. I think you know what dimension is, right? You have seen matrix, so you know that, right? Three dimensions, four dimensions. You just see all the three-dimensional objects and two dimensions and one dimension. You cannot see four dimension. All right, more than three, right? Can't see, right? All right, this has two coordinates, x and y, right? So how do you write that? So it has two coordinates. These are elements. So x belongs to R and y belongs to R. Yep, x and y belongs to R. Real numbers. X and y are real numbers. All right. So these are coordinates. These are the elements of this set, right? And you can show that this one also a vector space. Let's see. For if you consider n dimensions, right? That means you have how many number lines? N number of number lines. So this is, yeah, if you have 3 number lines, x, y, z, right? So this has 3 number lines. So this is 3 dimensions. Now we can talk about if you consider any point in this space R3, so you can write in this way x, y, z. So this is a point in this, this is an element of this set. This set is whole space, 3-dimensional space, right? So it has 3 components. Likewise, if you talk about Rn, so in this case you have n dimensions. So how many coordinates do you have? How many x1, x2 up to xn? So this time for this one, how many coordinates do you have? N number of coordinates. Here in this space you have 3 coordinates x, y, z, but for this set, for this space, you have n number of coordinates x1, x2, xn up to xn. Alright, so this is called ordered pair, right? This is called a pair. This is called a pair. This is called a 3 tuple. This is called, these are names. This is called an n tuple. N tuple. Here. Triple. Yep. And tuple. Yep. Here we go. Yep. So this is called a pair, right? This is an element of this space or this set, right? 2 space, 1 space, 1 space is real number line. 2 space graphically infinite plane. 3 space, yep. This one is our space. It has 3 coordinates, right? So this is called triple. Yep. No. This is 3 tuple. Called triple. Yep. So if you have n, let's say Rn, n dimensional space. So if you consider any element, an element, say this is an element in that space, xn. So we give a name. This is called n tuple, right? Those are not important. N tuple, right? But for space, I think this makes sense, right? Can increase the dimension up to infinity. If you have r infinity, that means you have infinitely many coordinates. All right. Likewise, right? Okay. These are, we can show these are vector space. So let's see how, right? Now we are going to, yeah, this is n tuple, yeah? Yeah, this is an element of this space, this set or space, right? So n tuple can be viewed as a point as well as a vector here. So yeah, if when it comes to 2 dimensions, because you are all familiar this 2 dimension, 3 dimensions, right? Right? Let's consider a point, an element, right? So x comma y is an element of r squared or r cross r, or anything, r squared, let's say r squared, right? So this is an element. So this is a point of this set or infinite plane. This is an infinite plane, right? Or anything, right? Or you can say anything, right? Infinite plane. This is an element, a point on this plane, right? So you can view this as a vector here, right? So if you define unit vectors along these coordinates, you know these things. I is a unit vector along OX. This is the origin. This one is called origin, OX axis, and J is a unit vector along OY axis. You can define a vector. This is a vector. This has a magnitude. This has a magnitude as well as a direction, right? Both are the same, and you can view as a point or vector, right? All right, both are the same, right? So, similarly, an n tuple can be viewed as point in Rn space. So, x sub I as its coordinate, or you can view that tuple and tuple as a vector in Rn space with, yeah, both are the same, right? Point or vector. All right, so let's add these. Let's view this as a vector. Then it is easy because you have learned vectors in your A levels, right? So vector addition. Now we are talking about vector addition, right? So our set non-zero set is Rn or R2 or anything. R2 infinite plane or this 3-dimension or Rn. So these are the sets, right? So now we define an operation. We define operation, two operations on these set. Let's see how, right? So I think everybody are familiar vector addition, right? So you know that how to add two vectors, right? So let's talk about that, right? 8:30. All right, here vector addition. So how do you add two vectors? Yep, it is familiar to you, right? Because you have past A levels. So you x, this is your x axis, y, this is your u vector u, right? It has two components, u1, u2, right? And this is the next vector v. It has two components because we are talking about, this is an element of R2, right? This is an element, right? So this is your entire set R2, right? So this is one of elements of the set, right? This is another element of the set. V1, comma V2, right? Okay, when you add these two up, you get this kind of vector. Or if you complete parallelogram, so you get another vector, right? Vector addition, get another vector. That means when you operate these two vectors, so you get another vector. All right, you get another vector W, which belongs to that set. So we have given a special name. Do you remember? We have given a special name for this. So this set is closed. This set is closed under addition and addition, right? So let's learn that today, right? So, all right. So vector addition, you have to add corresponding uh, what, coordinates, right? So this one again. So here they are considering Rn vector space, Rn space. So this one belongs to Rn, right? So and they define another one, another operation. So here let's write this one in this way. So earlier, so how did you define this operation? So basically, let's define this operation. So basically, yep. So what is, so this set Rn. So first element belongs to Rn, and your second element belongs to the, yeah, same one, Rn. And when you operate, so that means, so when you operate these two, again you get another element in Rn, right? Rn. So I will write that one. U, when you add U, this is an element in this set. This is the operation we do, plus, and the second element UV. Right, this belongs to, this is again a vector in the same set I. So this plus is closed. This operation is closed under, yeah, this operation is closed. So we say this operation is closed. Now we introduce another operation. This is called scalar multiplication, right? Right. So here we consider scalars in real numbers. So we pick a numbers in real line, right? So C belongs to that set, right? C is a real number. So, right? So when you multiply this vector by C, again you get another vector, right? This belongs to Rn. So that means here lambda, let's say, let's put C. All right. That means you are, so here you have a vector U, right? This is your vector, right? Let's say your C is bigger than, greater than 1. So when you multiply, so you get another vector which is bigger than this vector here, because C, this scalar is greater than U. This one also a vector, another vector. You stretch this vector, right? If C is greater than 1, so you get another vector which the magnitude of this vector is bigger than this, right? If this one is smaller than 1, so you shrink that vector, just compress that vector. Again, this one also vector, right? So, all right, this one closed under this operation, scalar multiplication, because this is an element in R and space. So did you understand that these two operations, we define these two operations? So this is the vector addition, or we operate within these two sets. So this one is, so this operation is done within the scalar one and the previous space. So let's define, so this operation, the scalar multiplication, we perform this operation within these two sets. What do you get when you do this operation within these two sets? You get another vector in this element. All right, okay, this is the operation. Hi. If you perform this operation between these two sets, you get another you get another element in this set. Right? So we defined, so we had what we had initially we had Rn space, and we define this operation on this set, right? And also we define, here we have two operations, so this is called vector addition, right? So we define another one, this is called scalar multiplication. So this one, we perform this operation with this one and the scalar field R. So R is our field. So we call, right, so these are the operations, right? So basically we have two operations. One is vector addition. So this is performed between these two, between these sets, this one and itself, and this one is performed scalar multiplication performed would be performed between this set and the field R, the set R. All right, does this make sense? Are you following me? Do you have any questions? These are very important. So this is the pure linear algebra, right? So, yep. Do you have any questions? Does this make sense to you? Do you have any questions or any doubts? So let's move forward, right? So sum of two vectors and scalar multiplication of a vector in R are called standard operations. So we have defined two standard operations. One is between these sets. Another one is between this one and the field, the scalars, this field. This one also field. You will learn those things in third year. I don't know, right? All right. Get you zero vectors. Okay, let's go to the definition, original definition. Let me go to the original definition. Okay, this is the original definition of vector spaces. So there are how many? There are 10 conditions. We have to check whether it is a vector space or not. So let's denote V, right? So this is a non-zero set of non-zero set, not non-zero, non-empty set, right? Right, let's discuss this one now because I have limited time, right? So this is a this is a set, non-empty set, right? Non-empty set, and we define two operations, right? As we did before, right? Plus, so plus is defined between these, between same v and v, right? And we get another vector, another element which belongs to this set, and this is called, vector addition, and scalar multiplication. And we consider R is our scale, field, the field, right? Let's do it in abstract way. F, let me take F. So F is the field, right? So we perform this multiplication, scalar multiplication between F and V. What do you get? We have to get an element in V, right? Right. So this property, look at the first property here. The sum of, so these are two operations, right? So here you have two operations. You have a non-empty set with these two operations, right? Over the vec over the field f, over field f, right? So here you have v, non-empty set, this operation, and scalar multiplication over field f, right? So this one, okay, let's go from here. All right, so let's take any two elements of v. So v, simple u, and v are elements of uppercase V, right? So if you perform this operation, right? If you perform this operation, so what do you get? You get something in V. That property is called closure property, right? V is closed under addition. For instance, if you consider this set, the natural number set, right? You know, it has counting numbers, 1, 2, 3. Yeah. So this is your set. If you take any two elements in this set, if you perform this operation, that means if you add these two up, if you add, let's take any elements, right? A is an element of this set, and B again element of that set. So when you add these two up, this is normal addition, right? Normal addition. So again you get another natural number, right? Say, yeah, see, this one also natural number. This belongs to the set N, natural number set. So that means this set is closed under addition, right? Right? Look at this one here. Here, I will take this set here. Can you say so? A is a non-empty. It has two elements, right? This is a non-empty set. So I add 1 twice. So I perform addition Yeah, I add 1 twice. What do you get? So you get 2. Oh, 2 does not belong to this set A. So that means this set is not closed under addition. All right. Does this make sense? Did you understand? Are you following me? Do you agree with me? Or any questions? These are very important, right? This is the real linear algebra, right? All right. So we understood this one. All right. So if you perform addition within these sets, or if you take any two elements, if you perform this addition, then you get some element which belongs to the original set B. Right. So we have given a name for that. So this set is closed under addition. Right. All right, let's look at the next one. That means if you perform addition between these two sets, you get again V. Right. So this is called closed under addition. Right. All right. Now let's go to the next one. Now we perform multiplication between this field and the set V. Let's see whether we get an element which belongs to V. Let's see. So if it is, then it is closed under scalar multiplication. Let's see. So let's try to understand the second one using an example. Let me take this example. All right. Oh, okay. Let's take this one. Integers. No, natural numbers. 1, 2, the counting numbers. 1, 2, 3, 4. So this time our field is R. Right. So this is our field. Let's see if you perform. So we know that this one is closed under addition. Let's check whether this one is closed under scalar multiplication over R, right? Right. That means we are going to check. When you perform some element in R with no and in integer natural number with field R. We have to check whether we don't know. We have to check. We want to get that element in R. Let's check that one. Don't know whether this is true or not. Let's check. All right. So you know R. So it contains rational numbers. So half, 1/2. If you consider 1/2, that belongs to R. It's a real number. If you multiply this scalar, this number, by one of elements, say let's take 1. 1 is an element in R. So 1 belongs to R. 1/2 belongs to this. Let's perform scalar multiplication. Let's do this 1 times 1. What do you get? 1/2. Oh my God, this does not belong to your original n. So this is not true. That means this set is not closed under scalar multiplication, right? Right, this set is not closed under scalar multiplication, but this set satisfies this condition, commutative property. So if you consider any two numbers in this set, you can swap those two numbers, right? So for instance, 10 is a natural, or 1 is a natural number, 2 is a natural number, you get 3. If you swap these two, again you get 3. This property. This is true for all AB, UV elements in this set. But so we can say this. So this set satisfies commutative property, right? I think we have discussed commutative property before, right? And also this one as well. This set satisfies associative property. So you can, right? I think you understand. We have discussed this one, I think, on the first day, right? So you have to check this condition as well. First, you have to check this one, whether this operation closed under vector addition and addition, whether this, when you perform this operation, whether, look, you have to check whether it is closed under multiplication, scalar multiplication, right? Scalar, right? And check these one, whether the commutative properties is true for this set, or V, right? V is our set, and you have to prove this one as well. This is called associative property. And zero element. So if you, you have to check whether there exists an element. You have to check whether there exists a zero element. That means zero element means there exists. Yep. So, yep. This one is an element in V. So if you perform addition with any other element, you get the same one. So I think you remember we have discussed this. This is called zero additive identity, right? Zero element, right? So you have to check whether there exists a zero element. Let's check that one. All right. Okay. And let's consider this one. This set here, 1 2 3 4 5 6 7, right? Natural numbers. So can you say, so yeah, this property is true, this one is true for this set. Let's say this one 0. So can you find any element in this set, say 0, such that when you add this one with any other elements, you get the same element A? No, right? It doesn't contain 0. So here we are talking about normal addition. So this set does not contain 0, right? Therefore, there does not exist 0 element in this set. So, right? So this is not a vector space, right? Okay. So for instance, Z, integer, set of integers. You know, set of integers, 0 plus or minus. Yep. You know that, right? 0 plus 1, 2, minus 1, minus 2, this set. All right, this has 0 here. All right. So this set contains 0 element, right? If you take and so this is the 0. If you add any element with 0, you get the same element. So in this set, so this set contains a 0 element, right? Okay, so we understand that. So inverse, other one is negative. Yep. Inverse, additive inverse. For every element for any element in V, there exists an element called additive inverse, so, or negative. Let's denote this, right? Such that this one is true. Let's find that. Okay. All right. Let's consider integers. Integers 0 plus or minus 1 plus or minus 2, right? If you consider any integer n, there exists, you can find -1 also an integer, right? So when you add these two up, when you add these two numbers up, you get the previous additive identity. This is the additive identity, and this is called, for any element in this set, for any element, n is an element, any element, right? So we can find, if you take this one, then this one belongs to this set. So when you add these two up, what do you get? You get additive identity 0. So that means this set satisfies this condition 6, right? So for every element of V vector space, no, the set V, there exists an element. If you take any element in this set, there exists an element in that set, such that when you perform addition between these two numbers, you get additive identity. All right, this one is true, right? So now go to the next. So these are addition axioms. So this addition performed between V and itself, right? This one performed between V and itself. So you had to check all these 4 conditions, right? And let's go to now it's time 9 o'clock. Yeah. All right. I had to finish this one today. Let me finish the recording.